In this video, we'll discuss diffusion models, the latest and best performing approach for generative AI to create images, audio, and content in many other modalities. Let's dive right in. Diffusion models. In this video, we'll cover denoising diffusion models. A denoising diffusion model consists of two processes. The first one is the forward diffusion process, in which one takes input, in this case here, an image of a cat, and adds noise to this input data gradually to, in the end, reach a state where the end result is really indistinguishable from Gaussian noise. The second process is the so-called reverse denoising process. That actually takes noise as input and generates output by denoising this noise. Now, why is this called diffusion? Well, this is based on the physical process of diffusion, where you have a state of high concentration of some material that diffuses to the areas with lower concentration of that material until the material in the end sort of has the same concentration everywhere. And the similarity here is our input actually has information, and that information diffuses until it is just indistinguishable from noise. Now, and this reverse denoising process, this is actually where learning happens. So the forward diffusion process, that is actually going to be fixed, and the reverse process, there we actually learn to undo this addition of noise in the forward process. Now, in a bit more detail, in this forward diffusion process, we sample from a Gaussian distribution, t times. So we take this initial input and we add a sample from a Gaussian distribution to add noise. We do that again and again and again. And this is a lot of times, maybe 1,000 times or so. So capital T here is something like 1,000, until we are indistinguishable from Gaussian noise. Now, each of these individual transitions is just sampling from this Gaussian. So this xt is sampled from a Gaussian with mean xt minus 1 multiplied by a scalar that is between 0 and 1, and this beta t is typically something that is quite close to 0. So you contract the xt minus 1 a little bit. So for example, beta t might be 0.001, and so you just add a little bit of noise and contract the previous xt minus 1. But so this beta t, that's actually not fixed, but actually it is increasing over the course of the diffusion process. So with larger t, the beta t actually increases. So this forward diffusion process is a stochastic process, and in particular, it's a Markov process, meaning the future is conditionally independent of the past given the present. And that allows us to write this joint probability as this factorized product of these individual probabilities, where each of these individual terms is just this up here. So one nice property of this forward diffusion process is that because each of the individual sampling steps is just very simple, we can actually derive a closed form for sampling ahead many different times. So if we want to, for example, get a sample of x4, we could sample x1 given x0, x2 given x1, x3 given x2, and x4 given x3 individually. But we can also instead actually directly sample x4 given x0. And that we can do with this so-called diffusion kernel, which is written like this, and we will actually derive this in the exercise. So here, just very briefly, we denote by alpha sub t this 1 minus beta t, and by alpha bar sub t the product of these alphas, and then the diffusion kernel can be written like this. And as always, well, so this here is a Gaussian, and we can sample from Gaussians by, well, sampling from a standard normal Gaussian and then multiplying this sample by the standard deviation. So this here is the square root of the variance, and then adding the mean. And now, before I mentioned that the beta t's are not constant, but there's a schedule, and this schedule is designed such that this product of these alphas, so the product of the 1 minus betas, actually converges to 0, and that then this diffusion kernel of the final step given the first step actually is approximately a standard normal distribution. 0 mean, standard deviation 1, or in general, a diagonal covariance matrix with all ones on the diagonal and zeros elsewhere. Now this diffusion kernel, that gave us the conditional probability of xt given x0, but now also let's have a look at the marginals for individual xt's, not the conditional. And we can look at, so this diffused data distribution at step xt, so the marginal distribution at a given point in time. We can derive that by integrating the joint, and we can write the joint as the prior, so the probability for the first step times this diffusion kernel, and we can sample from this by first sampling from the prior, and in particular sampling, for example, an input image from our data, and then sampling from the diffusion kernel. So this is not a distribution that we'll have available in closed form, but we can sample from it. And if we now inspect what this diffused data distribution does over the course of the forward diffusion, we see that the initial distribution is quite complex, and this distribution gets ever less complex as we add noise over the course of the diffusion, and in the end, the noise distribution is just very simple. So, for example, we have these two bumps here. They slowly merge into becoming a single bump, and likewise here, these two bumps slowly merge in order to become a single bump, so getting ever simpler. So we can also use this one-dimensional example to look at what happens in the reverse process. So there we start by sampling our xt from this Q distribution, which is a standard normal distribution. So here we sample this from the standard normal distribution. We sample this point. And then we iteratively sample from this distribution Q xt minus 1 given xt, so backwards. And well, this distribution is unfortunately generally intractable, but we can actually approximate it with a Gaussian, and this Gaussian approximation is a good approximation if this beta t is small enough. So locally, this is a quite good approximation, and that is why the beta t shouldn't be too large. You know, if the beta t is large, and for example 1, and we directly go from our original distribution to noise, then there is no way that we can directly from here get our original distribution back. But if the individual steps are small enough, then there's hope that we can learn to undo this noise addition. And this is where learning is going to happen here. So we're going to parameterize this Q distribution as a normal, and the variance of this normal distribution, we could also learn this, but typically this is taken as fixed. And the mean of this distribution, this is now going to be having trainable parameters. This is going to be the output of a network. Now, the same visualization here, again in the space of images. So the reverse process samples from a Gaussian t times. You sample the noise vector from a standard normal distribution, and then iteratively you sample from your reverse process. Then this reverse process has a trainable network that in the space of images typically is actually a UNet, because it takes an image as an input and has an image as an output. Now, the training procedure for these diffusion models is actually in some way akin to the training of the variational autoencoder. In particular, there's a variational upper bound involved that upper bounds the expected negative log likelihood of your data under your reconstruction by this term here. This is similar to this evidence lower bound that we saw in the variational autoencoder, but I'm sort of consciously glossing over the details here because we don't want to spend too long with this derivation here now, but there are several references that you could look at if you want to really understand this in detail. But for the sake of this lecture here, suffice it to say that this variational upper bound here, this L, consists of 3 different terms, out of which the L capital T, that's a so-called prior matching term, and that's independent actually of the theta. So that's not going to be that's not going to matter for our learnable parameters. Then this L0 is a reconstruction term, but that's just the final step of the reverse process. And this LT minus 1, that's really the main term, because this is going to be added over all the 1,000 steps. Okay, so the main term to minimize is going to be this L sub t minus 1. And that's a KL divergence between this true backwards distribution and our approximation thereof. And both of these parts are actually Gaussian, and we can choose the variance of our approximation to be the variance of the true reverse process. And in that case, actually, the KL divergence has this very simple functional form that can be minimized by simply minimizing the squared difference between our prediction and the true mean. Now, this true mean is actually of the following functional form here, where you have a sampled noise vector, and that's multiplied by this constant, subtracted from the true xt, and then multiplied by this constant. And we can mimic that by also making our prediction have the same functional form, where we predict the noise and then multiply it with the same constant subtracted from xt and multiply that with the same constant. So this might look like a pretty complex parameterization, but it actually gives rise to a very simple algorithm in the end. And this algorithm, in a nutshell, tries to minimize this one overall loss here, where this loss is basically an expectation over different time steps sampled from a uniform distribution between 1 and capital T, different data points from our empirical data distribution, and different noise values coming from the standard normal. And in expectation over all of these, we're trying to basically predict our noise with this L2 loss here. And so this E sub theta, that's a neural network that takes as input the current image, xt, which we get from our diffusion kernel by from x0 in a closed form. And yeah, and so this neural network is really trained to predict how much noise was added to this particular image in order to basically then subtract that noise and get back an approximation of x0. Now this might become a bit clearer by actually looking at an algorithm. So we're trying to minimize this loss from the previous slide. And we do so because it's an expectation over various quantities. We do so by sampling these quantities. So we sample time step from the uniform distribution, we sample a training data point, and we sample a noise value. And then we simply compute our xt by the diffusion kernel. So that's in the previous image, this was this 4 steps ahead sampling. So we sample t steps ahead in closed form, and then we take a gradient descent step on the squared distance between this noise and the output of our network. And so we basically learn to predict what the noise was. Visually, we can look at this as follows. So here we have our x0. We apply our diffusion kernel to this. So we basically multiply this with a constant and add noise multiplied with this different constant that was all in our diffusion kernel in order to get xt. And then this xt we feed into a UNet along with the time step t in order to predict noise. And this noise here we're going to compare against this noise here. And we're going to make these two here as close as possible. Okay, and when we have a network that can do that, then we can use it in order to sample new content from noise. So in order to do that, we initialize our reverse process from a sample of a standard normal distribution, and we iteratively apply our reverse approximation of the process by just applying this normal distribution with this mu sub theta. This is parameterized using this noise network. And then you also always add a bit of noise back. So in terms of an algorithm, this looks as follows. So first you initialize at the standard normal distribution, and then at each step, so you compute the mean of this distribution here. I'm using this parameterization via this noise prediction network, and then you get the xt minus 1 by using a sample from this Gaussian distribution, so this mean plus this standard deviation times the sampled epsilon. And you iterate. In terms of visuals, let's look at it like this. So at any given time, we have a current image, xt, we feed that into a UNet together with the current step t in order to get a prediction of what do we think is the noise that was added to this image in order to get to this. So that's the output here. We will subtract that output from this image to actually get a cleaner image, an image that has less noise added. And that is going to be this mean here. And then, of course, we need to add back a little bit of noise in order to have this proper reverse process that actually samples from a distribution. And then we add back a little bit of noise, but the resulting image here should be less noisy than the initial image. And then we iterate this over and over again until we are at the beginning and have a clean image. And this is the entire algorithm. The only problem here is that the diffusion process, the sampling at test time in order to generate a new sample, that can take a while because we need to go through these 1,000 steps in this for loop, and in each of these we need to apply our pre-trained noise prediction network. So sampling actually requires a fairly slow diffusion process. And that is brings us to a comparison of diffusion models with GANs and VAEs. So diffusion models are great in terms of getting high quality samples and also getting very diverse samples, but they're not very good at fast sampling. Both VAEs and GANs are good at fast sampling, and GANs can also get high quality images, but GANs have a problem with robustness and also with mode collapse. So they tend to sample very similar images. VAEs tend to be good in terms of diversity, but they tend to have somewhat blurry samples. So the quality is a problem for VAEs. So as I mentioned, diffusion models are slow for sampling, especially high resolution images, because there you need to go through this forward pass through this network with a high resolution image 1,000 times. And one solution to this problem can be to actually have a latent diffusion model that applies diffusion on the latent space of a VAE. The sampling there is faster if you use a lower dimensional latent space, and also as an added benefit, you can have embeddings of arbitrary conditioning contexts that you can integrate quite easily into this latent space together with the latent space of your that you're doing the diffusion on. As one example, you could, for example, have some textual prompt, then you can have a text encoder, and that can yield an embedding that you can put into a diffusion model in a latent space. So the diffusion model would again be a UNet conditioned on, then also conditioned on the text encoding, and then at the end, after the diffusion model, you could have an image decoder that then actually yields a generated image. And so this is indeed what's happening in a lot of the state-of-the-art models for combining diffusion models with other embeddings of, for example, of language, of audio, of whatever. For example, in DALL-E 3, you can actually write text that actually then goes through GPT-4, gets an embedding, and that embedding is being used inside of a diffusion model in order to condition the diffusion model to output a particular image. All right, that brings us to the end of this video. And as always, I'd like to leave you with a few questions to answer for yourself. And this is also the end of today's lecture. So looking forward to seeing you next time. Thank you.